In this video, we will identify the types of surfaces given the equation for each one. So here we have a big long list of equations in x, y, and z, and what we are to do is to rearrange them somehow so that they look familiar, so that we can identify them as one of the types of quadric surfaces or cylinders. So my rule of thumb for doing this type of thing would be to just sort of play with the equations and rearrange them in such a way as to try to minimize the number of minus signs. So it's not always possible to avoid the minus signs. You might have to end up with some negative terms, but I usually try to shuffle the terms around to the other sides of the equations to sort of have as few minuses as possible. So let's sort of try this and see where it gets us. So for part A here, I would maybe just move the 2y to the other side and get something like 2y equals 5x squared plus 4z squared. And you'll notice I've ignored the 4. Maybe let's move the 4 over to this side. It doesn't really matter. I said I was avoiding minus signs, but here I sort of want the 4 on this side. And the reason is, if you ignore the constant and just look at the first part, 2y equals 5x squared plus 4z squared. This looks like something we recognize. This looks like the equation of a paraboloid, an elliptic paraboloid. And since the equation is solved for one of the variables, in this case y, because it's not squared and it's on its own side of the equation, adding or subtracting a constant from the other side doesn't change the shape of the graph. It just shifts it up and down in the y direction in this case. So that minus 4 doesn't really change what type of surface it is. So in this case, this is an elliptic paraboloid. Okay, and again, the reason here is that one variable is on its own side of the equation and not squared, and the other two variables are on the other side of the equation and they're both squared and both positive. Okay, so on to part B. Let's multiply everything by x and get something like this. 5y squared minus 3z squared equals 2x. And again, I said my rule of thumb was to sort of minimize minus signs, but again, here I'm not going to do that because it already looks like something familiar. Right? We have one variable on its own side, and it's not squared, the x. And the other two variables are on the other side of the equation. They're both squared, and one of them is positive and one's negative. And this you should recognize is the form of the equation for a hyperbolic paraboloid, which is also called a saddle surface. Okay, on to part C. So here I'll actually use my rule of thumb that I said at the beginning. Let's try to just move things around so that there's no minus signs. So move the 2y squared to the other side. And here we should be able to recognize what this is. This is one of our standard forms. We have one variable on its own side of the equation, and the other two variables on the other side. All three variables are squared. All three have positive coefficients. So this we should recognize as the equation for a cone. Okay, on to part D. Part D looks a little weird because of this cosine. We have this trig function in there. But we actually don't care what shape this is or what it really looks like. The only thing that should jump out at you is that there's only two variables in the equation. There's no x. We're missing the x variable in this equation. So that tells you that this is a cylinder. So we're not going to rearrange this equation. We're just going to notice that there's no x in the equation. And if one of the variables is missing, that tips us off that this is a cylinder. Okay, in part E, let's move everything around so that we have as few minus signs as possible. So we'll move the y squared to the other side. And also let's move the 4 over too. So we'll, in other words, put the 3x squared by itself. So we get a negative sign on the constant term, but we've avoided all negative signs on the coefficients of the variables. So look at this form. We have one variable on its own side, and it's squared. The other two variables are on the other side of the equation, both squared, both with positive coefficients. And then we have a negative constant on that side of the equation too. And this should tip you off that this is a hyperboloid of one sheet. So we know it's a hyperboloid because one variable is squared on its own side and the other two are squared on the other side with positive coefficients. The fact that the constant term is negative when you put it on this side of the equation tells you it's one-sheeted. If that coefficient were positive, it would be two-sheeted. Okay, on to part F. Maybe first let's multiply the 3 to the other side. So we'll get something like z squared minus 5 is minus 3x squared minus 9y squared. And then maybe let's actually shuffle things around a little bit more, completely get rid of the minus signs. Let's move all the variables to the left and move that 5 over to the right. Rewrite it like this. And now we should be able to tell that this is an ellipsoid. And again, the way we recognize that this is an ellipsoid is that all three variables are squared, all on the same side of the equation, with positive coefficients, and that's equal to a positive constant. Okay, lastly, part G. Again, let's sort of shuffle the constants around to avoid negative signs on the variables. So what we get here, let's put the 3x squared on its own side of the equation. So 3x squared equals 4y squared plus z squared plus 4. So this looks just like part E, but now the constant is positive. And like we said there, that tells us that this is a two-sheeted hyperboloid.